beta-minus decay, where excess neutrons are converted into protons and producing electrons and electron antineutrinos. Red boxes above the line of stability undergo beta plus decay, where excess protons are converted into neutrons, positrons, and electron neutrinos. So for beta decay to occur, the parent decays down into the daughter state and populates it in an excited state. And it undergoes de-excitation by the emission of gamma rays. Gamma rays are emitted very promptly, so the half-lives are on the order of femtoseconds, so they're a little more difficult to detect. And as the daughter de-excites down to the ground state, there can be isomeric states, which are metastable. They have measurable half-lives, and these isomeric states can undergo further beta decay to granddaughters. And one important thing to note is the change in spin between energy levels. The spin of the state that the transition is into, for the type of beta decay that I'm looking at, those spin states are either the same or plus or minus 1 of the spin state of the parent level. So this is the ISAC facility at Triumph, which you might have gone to. The ISAC facility uses the 500 MeV proton beam produced in the cyclotron. So the cyclotron is over on this side of the site. The proton beam comes in, it's one of 2 targets, and produces spallation reactions and a wide variety of isotopes. These isotopes are ionized and directed through to a mass separator, where a particular mass with the charge ratio is selected. And this beam is then directed up into the experimental hall to different nuclear physics experiments. One experiment that I was part of is the API, and see here, this is one half of it. So the beam will come in from the left, and inside, hit a movable tape. And the beam will hit the tape and undergo decay, emitting gamma rays or electrons or beta particles, which are detected by these germanium detectors. These are high purity germanium detectors, and there are 20 of them in the 8-pi array. Each has a bismuth germanate Compton suppression shield, and this acts to reduce the Compton background from scattering that occurs in the 8-pi. So the experiment that I have been working on is the beta decay of 124 cesium into 124 xenon. And the goal is to look at the excited states that are populated in xenon. So for this experiment, a beam of 124 cesium was extracted from the mass separator and injected in or implanted into the 8-pi. And then we looked at the excited states and the transitions that came from the xenon. The 8-pi is an ideal apparatus to look at these kind of decays because it provides very high statistics, so we can look at weak transitions 220 new transitions, in addition to a couple hundred transitions that were already observed. And I also observed the two transitions that I talked about earlier, the low-spin transitions from Marinowski's paper. So in these two plots here, I have the counts, the event count rate on Y as a function of the gamma ray energy. So this 360 keV peak is very well resolved from this intense beautiful peak. So this is very impressive to be able to resolve these two peaks. And then over here I have this 289 peak, which is in a very low energy range of our data. And to be able to see this peak above this high background is very good. So once I have my level scheme built and I know all my transitions, I calculate the branching ratios. The branching ratio is the relative intensity of a transition to come from a specific level. So I have one level here, for an example. It's at 2204 keV, and I have 8 transitions coming from it. And in order to calculate the branching ratio, I use gamma-gamma coincidences again, like I was talking about before. So I use ratios of specific gamma rays that are in coincidence with each one of these. And by measuring the peak area of the gamma ray, I can then calculate the intensity of it. And then I go on to calculate the branching ratio by dividing the intensity of that particular transition by the total intensity of all the peaks. And in this table here, I have all my energies listed and the calculated branching ratio that I found. And I compared it to the literature values, and you can see 5 of the transitions that have not been seen before. So I've been able to get much more accurate for these transitions. So there were some unexpected transitions that we observed in this data set. So the spin state of the parent is 1+, and like I said before, the spin of the daughter is expected to be either the same or one higher or one lower. So the spin state of the ground state of Xenon is 0. So we saw these 6+ and 4+ states being populated, which didn't really make sense in our data set. But these states had already been seen from other experimental techniques. So we wanted to figure out why these states were being populated. So we went back and looked at the literature and saw that there is a 7+ spin state there's an isomeric state at 7+. There's a 6-second half-life in 124 cesium. And in order to see if this is what's populating our high spin states, we look at gamma ray decay half-lives. So looking at a specific gamma ray, we can look at its half-life and compare it to the half-life of the parent energy level. So looking at this 124 transition here, it's coming down from the 1+ state, which is a 30-second half-life. And by fitting the decay of it, we get a half-life of 30 seconds. And then we look at a transition that's coming from the 7+ isomeric state, and we have a half-life of 6 seconds here, which is the black curve. And then looking at the 668 peak, or transition, we also get a 6-second half-life. So we can then conclude that there is a new branch coming from this level to populate high spin states. And I should also say that this 7+ state is known, but previously thought to only undergo internal transition into the ground state here. And this decay branch was never seen before. So in summary, this data decay experiment produced a data set with extremely high statistics, which allowed us to discover over 20 new transitions, and especially the low spin transitions that were not seen before. And we're also able to find a new decay branch to populate high spin states. So my future work will include continuing to calculate branching ratios of all data levels and interpret these results to infer the nuclear structure properties. So I'd like to thank you for your attention, and I'd like to thank my supervisor, Paul Garrett.
Good time.